Start talking about pretty important topic in pre-calculus, and that's this idea of asymptotes, and they always show up in rational functions. So we better review what we mean by a rational function. When we talk about a rational function, we're really just talking about a fraction function. And we don't really just mean something like 1/4 x squared. That's not a rational function. Okay? We mean a function where I have two little mini functions over top of each other, like p of x over q of x. You know, a very common rational function would be something like f of x equals maybe 5 over x plus 2. That's a very common rational function, that type of situation where we have just a constant on top, just a regular constant number, and then we've got some type of function on the bottom. All right? So that's what we mean by a rational function, is a fraction function. And anytime we have these, if you remember in the fall we spent a lot of time talking about domain. And if you look at this function in particular, let's look at this one I just wrote. What number would not work? -2. If I put a -2 in here, it's going to give me a 0 in the denominator. So I know that x cannot be equal to -2 in the domain. Well, what we also know, and we're going to find out today, is that is also the location of an asymptote. All right? And the best way to learn about these is to consider them graphically. Let's consider f of x equals 1 over x. And what we're going to do is we're going to make a table, okay? And we're going to look at what happens to this function as we get really close to 0. Does everybody see on this function, if I was looking at the domain of this function, that x could not be 0? So let's look and see what happens to the function values as we get close to 0. We're going to go first from the negative side, from -1 to -0.1, keep getting closer and closer, -0.001 and -0.0001. And we'll use our graphing calculator for this. So if I go to the graphing calculator and put that function in, 1 divided by x. And if you remember, when I want specific x values, specific function values for a specific x value, it's better to go to the table setup and turn my independent variable to ask. Remember, the independent variable is 99% of the time x. So if I change it to ask, then I can put in the values that I want into my table. Make sure you've got your function entered, and let's go to the table now. I said we were going to start at -1. So I put a -1, and I hit enter. -1. Then we went to -0.1. Drop down to -10. Then we said we were going to do -0.001. Wow, we're at -1000. And let's do the last one that I asked for, -0.0001. See what function value we get now. Negative 10,000. Okay? So we went negative 1, negative 10, negative 1,000, negative 10,000. Negative 1, negative 10, negative 1,000, negative 10,000. So let's think about what that means graphically. If I look at the graph of this, here's negative 1, here's negative 2. We just started looking at some values. We started at negative 1 and we kept getting closer and closer to 0. At negative 1, it was negative 1. But then it dropped down to negative 10. You know, when we came over to negative 0.1, we're down to negative 10. Then as we got closer, I went to negative 1,000. I'm not obviously going to have room. But this thing, what it does is it just takes off. Okay? Takes off in the negative direction. Like that. Okay, as we get really close to 0, the function values just bottom out. All right? And we didn't look at the other direction, but let's just go back and just try maybe a big negative x value. Let's just use our head here a little bit. If I put in like negative 500 here for x, isn't that going to be a very small number? All right, so what happens here on the other side is this thing just gets really, really close to 0. It never crosses that x-axis, but it just gets really close to 0. Now, what do you think is going to happen? Let's come over and make a new table. And let's come in from the other direction. We'll start at positive 1, go to positive 0.1, positive 0.001, positive 0.0001. If I approach 0 from the right-hand side, what do you think is going to be the only change? Isn't the sign going to be the only thing that changes? Right? Because now I'm still plugging in the same x values, but they're positive. So if I go from the right, instead of negative 1, it will be positive 1. And instead of negative 10, it'll be positive 10, then positive 1,000, then positive 10,000. And so what happens as we approach from the right, if this is positive 1, as we approach from the right, this thing takes off vertically, like that. And as we go this way, it just approaches the x-axis but never crosses it. It gets really, really, really close to 0. And what you see now is this is kind of the base rational function. In the fall, when we were doing our function family, we called this the reciprocal function. And this function has two asymptotes. It has a vertical asymptote right here at x equals 0. It's an invisible line, if you will. If you think of Star Wars, it's like the force field. Okay? The function, most of the time, notice what I said, most of the time, not all the time, most of the time the function will not go across the asymptote. Every once in a while it will. And then look, we also have a horizontal asymptote right here on the x-axis. Its equation is y equals 0. This one is a vertical asymptote. I like to abbreviate those as a VA, VA, vertical asymptote, and this one is a horizontal asymptote. Horizontal asymptote, or we can call this one a HA, va and ha. Two new little pieces of information. The vertical asymptote and the horizontal asymptote. All right? Now, this is just the beginning of rational functions. These things can look all kinds of different ways. Let's look at another one. If we call this one number 1, let's look at number 2. How about f of x equals 2x plus 1 over x plus 1? Now, on this problem, where do you think our vertical asymptote is going to be? If we look at this denominator and say, okay, where is this thing equal to 0, and I solve it, yes, I bet there will be an asymptote at -1. So if I look at the graph of this one, let's go to the graphing calculator. The graphing calculator does not do a fantastic job graphing rational functions. I'll just tell you that right now. Now notice how we plug in this function. The numerator has to be in parentheses. If you don't, it will not graph it correctly. 2x plus 1 divided by the denominator also needs to be in parentheses, x plus 1. Okay? Now, if I just do a regular zoom standard on this thing, we see my function. All right? And once again, I have two asymptotes on this one. All right? We have one where we thought we would have one at -1, but we also have one up at y equals 2. So in your notes, let's just sketch a quick graph of this function and label it just so you can see the distinction. This one has a vertical asymptote at -1. But it also has a vertical asymptote through y equals 2. So the horizontal asymptote is y equals 2. The vertical asymptote is -1. And my function approaches both of those asymptotes. Notice the horizontal asymptote moved up 2 units. Okay? And I also want you to notice something. Look at this function. Do you see that the power of x on the top and the bottom is the same? Right? And do you also see that this is 2 over, isn't this kind of like a 1 right here? It's not written, but there's a 1 there, right? Isn't 2 over 1 the same thing as 2? And there's your horizontal asymptote. Okay? Let's look at another one. Trying to expose you to some of the different types of situations that we have. Number 3, f of x equals 4 over x squared plus 1. Now, look at that denominator. Is there a way the denominator could ever be 0? When I square something, isn't it always positive? So there is no way that this denominator could be 0. So you might be thinking, well, okay, so there's no vertical asymptote. But there is a horizontal asymptote. Let's look at this one real quick. Y equals 4 divided by the quantity x squared plus 1. This one only has a horizontal asymptote. I could look at it a little bit better if I closed my window down, maybe make it like -2 to 6 or something. See it a little bit better. Okay, so this function only has a horizontal asymptote. It's probably better sketched a little bit like this. All right? Only a horizontal asymptote. Only a HA at y equals 0. And we usually indicate those with a dashed line. All right, so it's possible for it to only have a horizontal asymptote. All right, so that just keep that in mind. How can we find the vertical asymptote algebraically? Let's make a note of this right now. To find, if I want to find a vertical asymptote, I just set the denominator equal to 0 and solve. My equal sign is a little bit messed up. See if I can't fix that. It's supposed to be an equal sign. Set the denominator equal to 0 and solve. If there is a place where the denominator is equal to 0, at that x-coordinate there will be a vertical asymptote. That's pretty easy. And we've actually done that a little bit before when we've looked for domain. But to find the horizontal asymptote, it's a little bit more of a process. If I want to find the horizontal asymptote, I have to look at the powers of the numerator and the denominator. Okay? So, let's write it this way. For the rational function f of x equals ax to the n plus bx to the n minus 1 plus so on and so forth over ax to the m plus bx to the m minus 1 plus so on and so forth. Now don't get all wigged out by all those letters and everything. Just understand what I'm writing here. I'm writing a polynomial function. Isn't this just showing that this is decreasing powers, like, 5x cubed plus 4x squared minus 3x plus 7, right? It's just another way of writing a polynomial, right, in a general fashion, because look, aren't the powers going down 1 each time? Same thing down here. The powers are just going down 1. But what we're considering and what we're interested with is the biggest power on the top and the bottom. And there's 3 rules. Okay? Rule number 1. If n equals m, and we actually just saw this example just a minute ago. If the highest power of the numerator and the highest power of the denominator are the same, then y equals, before I write this, I apologize, I need to change my letters here for a second, otherwise this is going to get confusing. Let's make those 2 letters C and D. Sorry about that. If n equals m, then the horizontal asymptote is automatically A over C. Okay, if the highest power of the top and the highest power of the bottom are the same, then it is just those coefficients. Y equals A over C is the horizontal asymptote. Doesn't matter. If the highest power of the top and the highest power of the bottom are the same, then the coefficients of those highest powers, that's the horizontal asymptote automatically. Okay? How about if n is bigger than m? If the highest power of the top is bigger than the highest power of the bottom, we like that one. There's no horizontal asymptote. Why? It does not exist. Okay. And number 3, the only scenario we haven't brought up is if n is less than m. Okay, so if the top power is smaller than the bottom power, then y equals 0 is the horizontal asymptote. Automatically, it's y equals 0. And we already found that out. Let's remember our first example. Remember this one? Didn't we find out that the horizontal asymptote was y equals 0? Right? Well, look. The top has a smaller power than the bottom. There's not even an x up there. We could say it's x to the 0 maybe. All right? Another example would be the one I mentioned here at the beginning, 5 over x plus 2. Okay? If it's just 5 over x plus 2, automatically there's a horizontal asymptote at y equals 0. Okay? We're going to do several examples here. Let's look at a couple. Let's say that you are asked to find the domain and the asymptotes. Find the domain and the asymptotes. Let's say that we had f of x equals x squared plus x minus 2 all over x squared minus x minus 6. And you're supposed to find where are the asymptotes, and we need to talk about the domain. All right? Well, we can just start finding the asymptotes, and that will kind of lead us to the domain. Remember how we find the vertical asymptotes. To find the vertical asymptotes, we set the denominator equal to 0. X squared minus x minus 6. We set that equal to 0, and we solve it. Looks to me like we're going to have two places, two asymptotes on this one. So I factor, and you can use product sum or you can just use backwards FOIL. I think backwards FOIL is easier in this case. X minus 3x plus 2. Split those up. Set x minus 3 equal to 0. So x equals 3. There's one of our vertical asymptotes. Set x plus 2 equal to 0. Obviously, that's going to be x equals negative 2. Both of those are locations of vertical asymptotes. Aren't those also places where x cannot exist, or where the function cannot exist? Those are places, if we're looking at domain, okay, x cannot equal those two numbers. All right? Now, how about the horizontal asymptote? Well, in this case, it's easier, isn't it? Aren't the top and bottom powers the same? Both of these powers are the same, so I look at my coefficients, which are 1 over 1. So the horizontal asymptote is y equals 1. Okay? And now we need to write our domain, because we were supposed to write the domain. So the domain would be negative infinity to negative 2 union, negative 2 to 3 union, 3 to infinity. Okay? Everything but negative 2 and 3 would be in the domain. And we have both a horizontal asymptote and we have two vertical asymptotes. Okay? Let's look at another one. How about f of x equals 2x over 3x squared plus 1? Well, same process. Let's set my denominator equal to 0 to find my vertical asymptote. My vertical asymptote is 3x squared plus 1 equals 0. There should be some light bulbs going off in your head because I've got something squared plus a number. But let's just go ahead and do it algebraically. 3x squared equals negative 1. Divide both sides by 3. X squared equals negative 1/3. Can I take the square root of negative 1/3? If I take the square root of both sides to try to solve this, there are no vertical asymptotes. Okay? We can't have an imaginary asymptote. Okay? So there are no vertical asymptotes on this problem, on this function. How about the horizontal asymptotes? Once you learn the rules, everybody likes the horizontal asymptotes because there's not a lot of work involved. Is there a horizontal asymptote? Yes, there is. Because the bottom power is bigger than the top power, so it's automatically y equals 0. Okay? And just so you know, we're not going to take the time to graph this function, but here's what the graph of this function looks like. It looks like this. This is an example where the function does cross the horizontal asymptote. The horizontal asymptote is right here on the x-axis. So it does cross it at one place, at the origin. But everywhere else, it never gets there. Okay? It gets really close, but it never gets there. Okay? One more type of problem. What if they ask you to write a function with the following characteristics? So they're going to give you some information like this. They're going to say, okay, there are two vertical asymptotes. One at -5 and one at 3. And let's say that there is a horizontal asymptote at y equals 0. Something like that. They want you to actually write the function. So you're working backwards. So watch how we do this. This really is not that hard. You take these vertical asymptotes, x equals -5, and you work backwards to where it was set equal to 0. Watch. If I add 5 to both sides, I have x plus 5 equals 0. And that is one of the pieces of the denominator. All right, so when I get ready to write the function, I'm going to have a fraction bar, and I'm going to have an x plus 5 here. And then I take the other asymptote, the x equals 3, and I do the same thing. X equals 3. I subtract 3 from both sides using an algebra step, and I have x minus 3 equals 0. So there's my other piece of the denominator, x minus 3. Now, if the horizontal asymptote is y equals 0, don't I just have to have a bigger power on the bottom than on the top? Right? Now, what's the power down here in the denominator? It's going to be x squared. So couldn't I have more than one possibility on the top? I could have, you know, something with an x, like 5x. Right? Or I could just have the number 5. Either way, I could have a possible function with those two vertical asymptotes and a horizontal asymptote at y equals 0. Okay? So you're working backwards on those problems. And we will stop there for today.